Okay, for this next example, we have a cylinder, no, a cylinder shaft with this 20 centimeter diameter with a uniform temperature of 600 degrees Celsius. And then it is cooled slowly at an environment of 200 degrees Celsius. So the heat transfer coefficient on average is 80. And we need to determine the temperature of the shaft or the center of the shaft after the start of the cooling process. So also determine the cooling heat transfer per unit length of the shaft during this time period. So in order to really do the analysis, no, or to solve this problem, we have to check first if the byte number is less than zero point 0.1. So it might be much more simpler. The solution will be faster if the byte number is just less than 3. So we can solve first for the byte number, which is just HLC over K. So the H here is given, the K is given. The LC is what, no? So if this is the diameter, then the LC, well, the characteristic length, or you can call this RC if you want. The RC is, or I'll just write LC here, is 10 centimeters. So again, this is just the distance from the center to the what do you call this, to the surface. So you can solve the byte number. You have H is 80, and then you have 14.9, and then you have 10 centimeters, so 0.10 meters. So, okay, so the byte number can be solved. Use a calculator. So 80 times zero point 0.1 over 14.9. So you have 0.53, no? 0.5369. 0.5369 as your byte number. Now, this is less than 0.1. Therefore, we cannot use the lamp analysis, no? So this is not a lamp system, no? Not a lamp system. So therefore, we cannot use the lamp system analysis. We need to use the more complicated one. So to find the temperature, no, we need to, yes, we need to find the temperature at the center. So if we say at the center, well, this is basically x is equal to 0. So to find the temperature, okay, so sorry, temperature of the wall, which is T of xt. So let me just write this down. Okay, which is equal to what? For cylinders, you have A, sorry, I always forget this. You have, you have, yes, you have AE, no? So AE, so A1E is to negative number 1 squared tau. And then you have, I think this is, I don't have the notes for, sorry, I'll just give you this one. I always forget this formula. Oh, so you have this, this Bessel function. So you have the Bessel function, JO, and then you have, I think this is the lambda, and then you have R over RO. Okay, so what are the given? What can we find? So we want to find the temperature. So basically x is equal to 0. So we have sorry, this is not the one that we're looking for. We have x given. The time is given. So time is 45 minutes. And then you have the environmental temperature 200. No. And then the initial temperature is 600. The tau can be found, no? So you have thermal diffusivity, and then the time, and then over K. Okay. Over L pala, no? Over L squared. So we can find this. And then, I forgot the one. So we know that the R, actually it should be R, no? Forgot the others. It should be the R. So the R here is actually given as 10, actually 0 pala, no? Matrix. So R is equal to 0. sorry. So r is equal to 0. So this will be okay, okay. So we can find this one using the table. We can solve for the temperature. Okay. So let's find first the Fourier number. That is thermal diffusivity times the time over L squared. So the thermal diffusivity is 3.95 times 10 raised to negative 6 meters squared per second multiplied by time. So this should be in seconds. So 4 to 5. I'll write the units, no? And then you have 60 second per minute. So that you can cancel this. And then the L here is 0.1 in meters. So this will cancel out. Everything will cancel out. It's squared pala to, no? This will cancel out. Second, minute, minute. Okay. So dimensionless tau can be solved. So this should be greater than 0.2. So 3.95 is 10 to the negative 6 times 45 times 60 over 0.10 squared. So you have 1.066. 1.0665. No units, no? So this is greater than 0.2. Therefore, we can use the analysis for the one-dimension transit conduction, the simple one. Okay, so we know the tau. We need to find the eigenvalue and the coefficient. So the Biot number is 0.5369. So at this value, we need to find the lambda, the eigenvalue, and also the coefficient. So we can use again the table, no? So you can see my playlist here. Where is the PDF? Yeah, wala. So you have 5369. Ayan, 5369. So in between these two, and syempre naka-cylinder tayo, no? So this should be used. So you have 9408 and 10184. Okay, so we can just use our calculator directly. So you have here 0.9408. Okay. Mode 32 pala, no? Mode 32. And then you have 0.5 and 0.6. Then 9408, 0.9408 and 1.0184. And then shift 155. And the value is 0.5369. 0.5369. So 9694. 0.9694. For the coefficient here, need to use this coefficient here. So 1.1143. So I'll just edit this. You can edit this in the data. So you can just change this. So 1.1143 and 1.1345. Okay, and then shift 155 again. And then 0.5356. Tama ba? 69 ba? 5369. So 1.12, 1.1218. So we got everything in place. We can solve now for the temperature at the center. So the temperature at the center, T of 0, at this given time is equal to, so let me just reconfigure this, guys. No? So this will be equal to T infinity plus you have Ti minus T infinity, then you have A1 e raised to negative lambda squared tau Bessel function of lambda. No? So actually this will be 0. So since this will be 0 over R0, we can just cancel this, no? Since this is just 0. So we just have to evaluate this portion. So to find the temperature at the center, So be mindful, this means center, no? Okay, so this will be, the infinity is 200 plus Ti is 600 minus 200 times 1 point, parang mali pala yung nakuha ko number, no? 128 pala to, no? Should be this. 218. 1218. Then you have E, and then raised to negative lambda 0.96. Ay, nakastat pala tayo. 9694 times, sorry, square pala to, no? Times tau, so 1.0665. And then that's it. So you have 364, 0.71. So 364.7, no? So this is in degrees Celsius again because it is a difference, no? Difference in between. Okay, so what's the next thing we should do? The next thing we should do is to find the heat transfer per unit length. So during this time, if this is during this time, we need to do the fractional, no? Fractional heat, fraction heat. So you need to use the formula Q over Q max is equal to, so I think this is 1 minus 2. I always forget this, so I'll just look at my notes. Theta cylinder, and then you have the Bessel function, lambda 1 over lambda 1. Right. So this will be, I mean, this can be solved, right? So the Q max can be solved. We can solve this. We can solve this. We can solve this. So this is given. So for Q max, what is Q max? This is just MCP delta T basically, you know. So Q max is Ti minus, sorry, it should be Ti minus T infinity. So the Q max is, so do you have a mass? We don't have a mass, but we have a density, no? Density and volume. So we can write this as density times the volume. So you have pi r squared each, no? So pi, actually, this will be just pi over 4 t squared each. Yeah. This is the volume, then density, and then Cp Ti minus T infinity. So this will be equal to 79. Then pi over 4, T is equal to 20 centimeters. So 0.2 meters. And then squared. So the height, the length, no? So we're assuming per one length, no? So we'll just multiply this by 1 meter. And then Cp is 477. And then Ti, so 600 minus 200, T infinity. So let's do a unit analysis here, kilogram per cubic meter. This is meter squared, this is meter. You have here joule per kilogram Kelvin, and this is Kelvin. So this will cancel the kilogram, meter cube, and meter squared, meter, and the Kelvin. So what's left is the joule. Where's the second? Don't have a second here, no. Per, ano nga pala to, no, per time. So we have to divide this by, forgot to divide this actually by time. So that this will be in watts, no? But anyways, it is in joules, no? The solution is in joules. So I guess we will just, we can just find in oh, I forgot about this, no? The formula should be in Q only, not in power. In energy format lang pala. But anyways, so this should be in Q over Q max. Therefore, we can solve for the Q max. Q max. So Q max natin. So 79 times pi over 4. Sorry, 79 pi over 4 times 0.2 squared, and then 477. Then 600 minus 200 is 400. So it's very large. Why is it very large? So we have to convert this in kilojoules because it is very large. So this is 47. Let's just write this in kilojoules, no? So 47354. 47354 kilojoules. This is the maximum heat, no? And then for this one, so we need to solve for the theta. So for the theta, we can just use this one. So sorry, it is not the wall. It is a cylinder. So this will be the theta of the cylinder, which is 364.7 minus 600, sorry, 200 over 600 minus 200. So ito na yung theta cell. Okay, sige. Oh, we are almost there. 364.7 minus 200. So 400 na lang. So 0.41175. 0.4118 na lang. And then lastly, we have the Bessel function. So for the Bessel function, we have to look at the lookup table. So we need to evaluate the Bessel function of the first order for lambda. So 9694, 0.9694. So using the table, you have J1 here, and then you have 9694. So we are in between 0.9 and 1. So the answer should be in between these two. So you just use linear interpolation. No? So again, we have mode 32, 0.40 as a 0.9 and 1. Point 4059. 0.5. And then 0.44. So shift, sorry, AC shift 155. And then 0.9694. So ito na yan. We have 4296. 4296. So this is equal to 0.4296. Yeah. So therefore, we can solve this now. The Q over Q max. So Q is just equal to Q max multiplied by 1 minus 2 theta cell. And then you have G1 of lambda over lambda. Lambda 1. Okay. So substitute the values. You have 47,354 kilojoules, and then 1 minus 2. So theta cell is 0.4118. And then you have the Bessel function 0.4296, and then the lambda is 0.9694. So use the calculator. 47,354. This is its stat. 47,354 multiplied by 1 minus 2 times 0.4118 times 0.4296. 0.9694. So the answer is 30,070. So Q is equal to 30,070 kilojoules. Okay. So we got it right. So we are off by a little value, no, but I guess the textbook rounded it off too much. So the answer is 30,000. Okay. So that's it. Thank you guys for listening.